Hey, welcome back everyone. So I'm going to be announcing our next session, I believe the final session for the day. We have Rob Bradford is working on integrating WebAssembly with Red Panda at Vectorize. He's been working with distributed systems for 8 years and C++ for his entire professional career. Previously, he helped Vectorize CEO Alex found Concord.io, which built a stream processor from scratch written in C++ on top of Apache Mesos, and helped build an IoT pipeline at Akamai, following its acquisition of Concord.io. Vadim is a software engineer at Vectorize, where he's working on a new inline transformation engine via WebAssembly. He has 3 years of experience in distributed systems. Previously, he worked on the core product at ClickHouse and contributed to databases and a cluster management system for VK, the largest social network in Russia. His areas of interest include databases, distributed systems, and formal verification via TLA+. All right, let's introduce our 2 speakers.
Hi everyone, my name is Rob, and I'm a software engineer at Vectorized. I've been here for over a year now, tasked with the creation of a new feature we call co-processing, which is an umbrella term for any ad hoc user transforms that execute on a Red Panda cluster. In my past work experience, I've been mostly focusing on projects that deal with functions as a service. First starting with Concord.io, a stream processor written in C++ on top of Apache Mesos, then moving on to Akamai, where I contributed to a similar type of feature within MQTT brokers.
Hi everyone, my name is Vadim, and Rob. We work at Vectorize.io. We're a C++ developer and contribute to the Panda transformation. Let's give you some high-level overview for that. How do users usually work with Red Panda? For example, they can have apps which produce some event inside Red Panda. Red Panda is event streaming platform. And also they have backend, for example, on Python, which consumes this data, transform it, and write it back. So we want to allow user run their function inside Red Panda without Python backend outputs. In the second part of our presentation, I would like to give you some ideas about WASM. WebAssembly, or WASM, is a binary instruction format for a stack-based virtual machine. One important thing is virtual machine is processor, but it does not exist. It has been designed to compile to a lot of architecture. The main goal for WASM is safe, provides sandbox for execution environment. Also, it's really fast because it tries to take advantage of common hardware capabilities, and also it supports non-browsing bankings. You can use a lot of runtime for WASM. Let's move to the next part of our presentation. It's how to work with WASM. People can want to use different languages for their function. So first things which they need is to change to compile their code to WebAssembly. For C++ and C, you can use MS-scripting framework. And the next thing which you need is WASM runtimes. For C++ and C, you can use different WASM runtimes, but my favorite is WASMer and V8. Before we started to develop WASM engine inside the Panda, I had done some comparison between WASMer and V8 because we wanted to choose like the best framework for that. So they have the same speed, but V8 need less memory than WASMer. And also one important thing is V8 not only WASM runtime, it also supports JavaScript. So for our first presentation, we use V8. Let's combine WASM and Red Panda. As we know, Red Panda is a event streaming platform. Is job in replacement for Kafka. it uses thread core architecture. For that, we use a star framework which pin thread to different cores and run copy of Redpanda on each thread. The idea we want to provide for user like tools for deploy their code in Redpanda and waste some time for run that. Some of our engine ideas. First of all is a sync engine. It looks like Node.js process which communicate with Redpanda. Redpanda send data to Node.js. Node.js apply transformation and send answer to Redpanda back. The second is inline transformation. It will use V8's runtime inside, and we want to delete communication between Redpanda and external process in this engine. The implementation of this engine is data policy. I want to give you some detail about V8 and some problem which we solved. First of all, V8 has some things like isolate. Isolate is copy of V8's runtime. Each isolate has on heap, garbage collector, and etc. In each isolate, you can create context. Context is execution environment. But one thing, you cannot run different contexts from one isolate in parallel. So, secondly, after that we implement execution for JavaScript and wrappers for data from C++. Execution process. The simple idea is you can run V8's runtime in C** application, but if you run while true, stuff like this, it block thread and Redpanda cannot do anything else. So to fix it, we implement executor. It is the thread, and also we add workflow queue for communication between C** and non-C* application, non-C* code like is the thread. C# cores, C# apps can put tasks to this workflow queue. Each task has time limit, and we use timer for stop task. Task is primitive communication between C# app and its thread. Each task contains some methods. GetFuture will return future in C**, which will wait done call. Cancel run terminate execution from V8. It generates exception and stop V8 delete. Process the main task function, which will be run in C thread, and done is final methods which signal C* that C thread complete this task. Also, Redpanda read data from topic, from disk, and it batched, and we want to pass record with batch. We want to pass batch with records to user code. But how user can communicate with these things? V8 provides some interface for that. You can wrap your data from C++ to object and put some methods and fields for that. For example, our record batch object contains size, which and contains successor. You can get record by using index. Also, each record is just map, and you access some value and key. And also, you can produce new transform record to this object. And after that, it will return new data to user. The policy is a tuple which contains some information about the connection, like user, ICLs, DL, and other things. It will help Redpanda understand who work with that. And the main pipeline looks like you want to read some data from Redpanda, And Panda reads this data from disk and try to find the policy. For that, we have mapping from topic to the policy, and for the policy contains tuple and also waits on time. And if we find the policy for current connection, we apply V8 information and return transform data to user. That's all. Thank you so much.
So now we'll talk about the current status of the co-processing beta. As it stands today, we have an async engine, which is the first iteration of the WASM engine. It's a Node.js sidecar process deployed by Red Panda. There's one per Red Panda node in a cluster. We have the pacemaker, which is the meat and potatoes of co-processing. It's all of the plumbing that routes data to and from the engine. And then we have some additional utilities to deploy and remove and query co-processors, which are all Kafka API compliant, meaning that with a No More Kafka producer and knowing the record format, you could deploy a coprocessor with your own tool. Our first implementation of the pacemaker was one run loop per core. We immediately realized that this wasn't the right implementation. Time was being wasted waiting on I/O when the C-star reactor was ready to perform some other work. So we eventually decided on having one run loop or fiber per coprocessor per shard. This means that the coprocessor API can still remain single-threaded with respect to partitions, while still exposing a higher level of parallelism. With this change, fibers can now interleave their requests to read, write, and send process requests and responses. We're pretty happy with the performance, and we'll keep this implementation for the time being. And what about state and failures? Coprocessing maintains the same at least once guarantees as Red Panda itself. Each fiber must maintain the last read offset for each input topic. And this is configurable. The API allows users to select where to begin reading, from the earliest offset, latest offset, or last stored offset. Now I'll talk about an example flow of how to-be transformed data moves to Red Panda. First, a user will deploy their coprocessor with RPK WASM deploy. Like I said earlier, this can be done with normal Kafka tools. All RPK WASM deploy does is binary encode the coprocessor and produce it onto a topic called coprocessor internal topic, with some additional record headers containing coprocessor metadata such as name, description, etc. Red Panda is always listening for events on this topic. Once it determines a new record has been produced onto this topic, it's parsed and the raw binary is sent to the Node.js engine. The Node.js engine will attempt to interpret the payload as the source code. If this is successful, it will parse the input topics and offset configurations, sending this response to Red Panda. Partition references to the input topics are then fetched. These references could be used to read data from a partition at a given offset. Then, all fibers and run loops are started. Data is read from the partitions and sent to the Node.js sidecar. Responses are interpreted, and data is written to the materialized logs. So, where do we go from here? As Vadim mentioned, we have ideas for new types of WASM engines. They should be able to be swapped without having to make major changes to the pacemaker. At this point, the pacemaker is bottlenecked by the WASM engine, especially since there is only one Node.js or WASM engine per Red Panda node, and it is single-threaded. However, we do want to test some of the limits of the pacemaker, such as how many of these fibers is too many? How big will some of the lookup maps and associative containers become when there are hundreds, thousands, tens of thousands of scripts? Is there a large compounding factor depending on the number of partitions and replication factor of the input topics? What about interleaving topics, etc.? Then when the WASM engine is finally embedded in the Red Panda process, there will be many questions about performance considerations, work fairness, sharing, ease of use, and of course security. We of course want to achieve all of these considerations while being as performant as possible, and it will be interesting in seeing what type of balancing act will be needed to be performed across all of these inputs to achieve a solid and dependable functions as a service implementation. Thanks for listening to our presentation. Have a good day.
Okay, all right, so let's jump into the Q&A. I guess Rob and Vadim, are you still there?
Yeah, how's everything? Still here.
Awesome. All right, so we do have a question. So the first question is, what is an RPK? You mentioned this in the presentation.
I guess I'll answer this one. RPK is short for Red Panda Keep. It's a command line client for all things dealing with Red Panda. It's our Go tool. It's open source, and you can use it to do things like produce and consume to the cluster, interface with the Kafka API, etc.
Awesome. All right, we still have questions coming in. So the next question is, does the stack-based model put constraints on potential performance? Are there plans to change, upgrade from the existing model, registers, GPU, etc.?
Do you want to take this?
Yep, you can take this
Like
question.
maybe. Okay. Plans to change, upgrade from the existing model. So currently, our model is first we're going to write this in Node.js, pure Node.js. Then we're going to migrate to embedding WASM engine within Red Panda, and then and currently we have an example with this. However, it's single-threaded, and then we're going to move to maybe putting one per core, one per shard, as we say in C# world, and maybe experimenting with different kinds of features within V8, like context and stuff like that. The idea is, if someone's code crashes, we don't want to really affect other clients. We want a degree of isolation, safety, and performance, and we have to measure all of these metrics together. So there's still a lot of experimental research we have to do. Yeah.
All right, so just remind everyone, we do have Rob and Vadim here live with us to answer your questions. So please drop them into the Q&A space here on the live chat. So I guess I have a question in terms of WebAssembly. So far you've kind of integrated. What have been some of the biggest challenges so far, and what type of extensions do you see people writing for the platform?
I think the big challenge of implementing WebAssembly is, first of all, you need to choose the right runtime. You need to choose the right engine for this, because it's a lot of, and you need to don't use a lot of memory and use a normal speed. So first of all, challenge is provide some testing and get the best choose for us. And also, frankly speaking, C++ API for WASM is not so very pretty and very clear. So you need to spend a lot of time to understand it and understand how it works, how you can stop engine, how you can catch an exception, and other things. So.
All right, our next question is, why the V8 engine?
I think I can ask about it. We compare it to WebAssembly engine is V8 and WASM.io. And V8 is not only WebAssembly, it's also support.js. So V8 contains a more function. You can set some constraints for environment for your code. You can set some constraints. You can add templates for your object, which you want to get from user from their function. Also, you can stop this engine and other things, which help us a lot. And another WebAssembly engine doesn't support it. So.
I also think that there was just a greater deal of maturity within the project. So when we evaluated WASM and V8 and some other options, that was a big factor in our decision as well.
All right, so I think we're getting close to time. If there's any other thing that you would give guidance to any other project maintainer thinking about embedding WebAssembly into their project, what would be some of the big gotchas where you think them to consider? Should they still, use WebAssembly, something like Lua, a better extension engine? What are your thoughts now after have gone through this?
Yeah, this is kind of like an experimental area right now. We're in the broader zone of function as a service. And how do you just take this random binary and execute it? There's so many things to think about, right? Like security and fairness and performance. WebAssembly is, at the cutting edge right now. It may be part of Web 2.0. So it has a lot of movement moving forward. We wanted to take something that would be popular and fast, and that had support for a lot of major languages like C, C++, JavaScript, and Rust is also another big one. So that was pretty much the biggest factors for our decision-making process.
Awesome. So I think that brings us to our time. I want to thank both you and Rob and Vadim for your excellent presentation and also spending time with us to ask them their questions live. If people have further questions, where can they find both of you?
You can reach me at rob@vectorize.io.
For me, it works too. You can send me a message and Vadim vectorize.io.
Awesome. So that brings us to the end of the day. I want to thank you all for attending today's open source Superstream on C++. We hope you learned a lot. Thank you again to all of our speakers and presenters today. We look forward to seeing you at more of our Superstreams next year. Have a wonderful rest of the day.